welcome everyone to today's session of this joint seminar series with John Hopkins and IIT Delhi, which is basically a series where we host talks related on topics which are topics related to intersection of scientific machine learning, mechanics, and the use of AI in mechanics. So today we have a very interesting guest, and it's my pleasure to introduce our speaker, Dr. Sathiskumar Ponnusami, in short, Satish. He's a reader, and which means associate professor in the aerospace engineering at City St. George's, University of London, UK. So Satish has completed his PhD at TU Delft in computational mechanics, followed by a postdoctoral research position at Rolls-Royce University Technology Center at the University of Oxford. He is a fellow of Royal Aeronautical Society, a fellow of UK's Higher Education Academy, and currently serves as an associate editor of Mechanics of Materials. His contributions has been widely recognized with honors including Airbus UNESCO Fly Your Ideas Award, NLF Dutch Aerospace Award, the Young Scientist Award at the International Conference of Self-Healing Materials, and many others. So Dr. Ponnusami's research team develops AI-driven modeling and simulation tools for aerospace and mechanical engineering problems with applications in structural control, failure prediction, health monitoring, and material design. He has authored more than 40 papers, 35 international conference presentations, 7 book chapters, and 2 patents. So today he's going to be speaking on machine learning-driven prediction and design for material systems. And with that, please, it's our pleasure to actually have you. The floor is now yours.
Thank you so much, Radhip, and thanks the core organizers of this SMaRT seminar series, Radhip, Sondata, and Savik. It's been a pleasure to present this topic. But before that, Radhip, thank you so much for the introduction. It's a great advertisement that you kept reading all the accomplishments. At some point, I became that's a lot. I became shy. So thanks for that. So getting into the topic, I think for the next 40 to 45 minutes, the objective is to bring you all together to explore what could be some useful applications of machine learning tools or architectures in the context of solid mechanics and materials problems. So that is basically the objective. Though the title reflects is a bit longer, the whole idea is, can we get some clarity on where ML might be useful? And in order that to be useful, how do we define the problem and how do we go about through the process? So that is basically the central theme of today's talk. So before getting into it, I'm a reader in City St. George's University of London. Just to give an idea of what this university is, it's in central London. It's part of the University of London as well. But if I just click further, you will see this person. I'm sure many of you would identify Mahatma Gandhi. He studied at this place. He did his law degree here. Also, Margaret Thatcher, one of the famous British prime ministers, also studied here. And also Jawaharlal Nehru studied here as well. And also others such as Muhammad Ali Jinnah and so on, Ambedkar, they all studied at this university in the law school. Okay, so with that, a quick overview of what we do for the last 7 years. I've been an academic for the last almost 7 years now, and my research is primarily centered around modeling tools for aerospace structures and materials problems. As you can see, there are 3 different pillars in this. In the first pillar, we primarily develop nonlinear modeling techniques to capture some of the highly intricate nonlinear mechanisms such as damage and buckling and the interactions in aerospace composite structures. That is what you see here. But also we develop techniques to control structure, either for morphing or for controlling the vibrations using SMaRT materials embedded into the structure. And also we developed high fidelity tools to capture impact-induced damage in aerospace composite structures. That is primarily in collaboration with Rolls-Royce. And moving on to the second pillar, it's all about modeling materials in the context of multiphysics and multiscale. And here we develop comprehensive modeling tools to develop novel material systems. For example, self-healing materials is what you see here, but also other classes of materials such as multifunctional composites for electromagnetics or stealth, and also in collaboration with Airbus, a range of material systems that can incorporate multifunctionality into it, such as harvesting energy and storing energy on top of being the primary load bearer in an aircraft structure. Now, the third cross-cutting pillar is probably the most relevant for today's talk, is about machine learning. It's a cross-cutting pillar, and in which we primarily work on two different directions. The first being utilizing machine learning architectures for constitutive modeling across a range of material systems, but also utilizing generative deep learning for design of engineering systems, both materials, but also more complex engineering systems. So what you see here is some of the examples, an end-to-end pipeline that actually takes in microstructure as input and provide the range of material properties of interest for design from a materials context. We also extensively use generative deep learning, primarily GANs and diffusion models, to come up with novel designs of rotor profiles to material systems. So that pretty much summarizes the landscape of my research team over the last 7 years. And this work is done not by me, but my students, by my postdocs, but also my collaborators across the world. So with that acknowledgement, let me quickly focus on the third pillar, which is machine learning for prediction and design. Within that, the first direction is predictive machine learning, in which what you saw in the previous slide is an end-to-end pipeline that can handle arbitrary microstructures to provide a range of material properties, multiphysics material properties of interest. And these are some of the results, which is also a key part of today's talk. But also along the second direction within this pillar is how can we use generative deep learning? I'm not talking about large language models here, but more of designing based on vectorized images and time series based image evolution. That is what I talk about here. And one example is what you see here is the training process of a Bayesian generative adversarial network, which can come up with or generate realistic rotor profiles for compressor systems. This is an industrial consortium funded project here. So what we really achieved here is a valid manufacturable rotor profile that is not designable using existing class of techniques. In other words, a lot of hybridization have gone into it. And as a result, we were able to observe certain profile designs which performed better than the existing benchmarks. So you may call that as hallucination, but you may also put it in a different context, that can you hybridize different classes of existing designs to come up with novel design, which is not otherwise possible using existing techniques. Yeah. So the second phase of the project is being funded now, and it's going to start in a few days in September. Okay, with that, this particular slide is quite important for me. Of course, you might see in the last 5 years, in fact, we are putting together a review manuscript on a comprehensive manuscript on machine learning applications for mechanics problems. And the growth of machine learning, applied machine learning manuscripts or articles in solid mechanics and materials is literally exponential. But then I've been working on this particular broad range of topics for a range of material system for over 6 years. But my fundamental questions are these. Where does machine learning add value? I think that is really, really important. And then once we identify, how do we design the problem and how do we choose the surrogate? Yeah, and surrogate is a very critical word here. The meaning should be properly understood there. And the fourth question is, what is really the way forward to integrate machine learning into mechanics problems, whether it is modeling or simulation or prediction? So how are we going to integrate machine learning architectures towards mechanics problems? I think if one is able to answer comfortably and convincingly for all these questions, then it would mean he or she has a nice problem to handle using machine learning. So with that, what I'm going to do for the next 40 minutes or so is I'm going to briefly touch upon 4 different problems which we have worked on for the last 4 or 5 years. And in the end, I'd like to critique in terms of which problem is more useful than the other. Yeah, in other words, One can always argue machine learning is simply a multidimensional intelligent curve fit. So how can it be useful for mechanics problem, which is rigorous physics and math based, right? So that is where answering these 4 questions are really, really important in my opinion. So with that, let us go on to the first example, which is on a surrogate machine learning based framework for multiphysics property prediction in composite microstructures. So that is a topic that I'm going to spend for the next 10 to 15 minutes. But the whole point here is, or the objective here is, how do we ensure while developing a machine learning surrogate to predict properties, how do you ensure it's useful? And what do we mean by usefulness? In my definition, the usefulness of an ML surrogate is when the model that you train is as generalized as possible. It can be interpretable. It respects physics as much as possible. And in terms of the deployment, it should be really useful for the design community. Yeah. So if we tick all these boxes, then one can say, okay, this is a useful machine learning tool. And such problems do exist in mechanics. Yeah. But there are a whole lot of problems that are not really amenable for treatment using machine learning. That is also something that we need to address and openly debate and discuss. Okay. So with that, let us go on. If you look into a typical material development workflow, you typically start with the requirements. Yeah, for a given structural component, you gather requirements in terms of the properties, both mechanical, thermal, and electromagnetic. What are the properties that you can think of? You put all the requirements, then you synthesize, you choose the route to process, and then you arrive at a microstructure, right? And this microstructure decide the properties. The properties can range from stiffness to strength to toughness to even thermal and thermomechanical properties. But then this is basically the flow of material development, in which if we can predict the whole workflow using physics-based tools, it's quite useful for design exploration, isn't it? Yeah, because you don't have to do a trial and error approach of developing new materials experimentally. Rather, you can use predictive tools based on physics to arrive at the correlations across these different cycles in material development. And in turn, you can optimize the whole workflow to arrive at the properties of interest and so on. But the problem here is using physics-based tools are good, but then they are actually time-consuming, computationally time-consuming, because remember, you have to model the process, you have to model the complex microstructure, and then you have to model the properties of your interest. So, and if you look into nonlinear properties such as strength or fracture toughness, it becomes even more complex in terms of prediction. So that is where can we bring in machine learning architectures to accelerate this process? And I'm using this word accelerate in a very careful manner. It'll be very clear towards the end of this presentation. So that is the single line objective of this particular piece of work, in which the overall methodology is what you see here. There is a typical workflow that you will find in any materials prediction framework using machine learning. You have certain microstructures of materials, and then you obtain the properties of the microstructures. There are 2 different ways to go about. One is conduct experiments, get the properties, or conduct numerical experiments, get the properties. And that is the most time-consuming aspect of generating the data set. But even then, can you still make a machine learning model that is still useful, despite all the computational costs associated with the data generation? And if you are able to say yes, then that's a success. Yeah. And of course, there are other aspects that you have in terms of if you do not use deep learning techniques, you may have to do quantifying the microstructure, do some dimensionality reduction, and then develop machine learning or train machine learning models to predict, followed by some sort of validation and interpretation of your models or the prediction from your models. Okay, so this slide is quite important here, which answers some of the questions that I raised before. And the title clearly says, how do we move towards a more generalized physics-respecting machine learning model? Yeah, to put it simply, the objective is simple. You given any arbitrary microstructure of a composite material. Yeah, I'm not saying that here you're feeding in a microstructure of a carbon fiber composite. No, you given any microstructure of any composite. For example, it can be glass fiber reinforced in epoxy matrix, or it can be a carbon fiber or any other possible fiber matrix combination. Yeah, you feed into the pre-trained model, it gives you the properties. Yeah, and here properties, I mean not just the mechanical properties, but a bit more, which you will see later. So some of the ingredients of the model that we developed are shown here. First one is it considers end-to-end practical range of fiber volume fractions, meaning the amount of fibers that you have in the system, and the different combinations of fiber matrix material systems. And that's quite key towards achieving a generalized model here. And obviously account for arbitrary fiber shapes and distributions, which is quite important to enable the design exploration of this particular space. And you just don't predict the Young's modulus or Poisson's ratio. You predict a whole range of properties of interest, starting from Young's modulus, but also yield strength to thermal expansion coefficient, to thermal conductivity, even electromagnetic properties and piezoelectric properties, for the reason that if you look into demanding applications in the structural context, take aerospace structures, you often do not just need one effective property such as strength or stiffness. You need a whole other lot of properties such as thermal expansion coefficient, thermal conductivity. In some cases, the material might be smarter. You may look into piezoelectric properties. You may look into stealth properties that is directly related to the electromagnetic absorption of that properties, right, of the material. So in that sense, you need to have the prediction space as wide as possible in terms of the properties of interest. So that is something that we accounted for in this framework. And obviously, where possible, can the model respect physical principles? Yeah. So that is another thing. Obviously, in the end, is my model understandable, first of all, to me? Do I understand what the model does? Yeah, because that basically is a significant step that you need to undertake in order to convince people who want to deploy such tools in practice. Okay, great. So these are some of the microstructures that we could generate using the in-house algorithm that we have, in which we can handle arbitrary microstructures of different shapes, different volume fractions, but also both in 2 dimensions and 3 dimensions. And of course, some of the classical microstructures are already validated with experimental micrographs, which is not shown here, but then it is already validated in terms of the following question is addressed, in the sense that we are generating microstructures virtually, but does it correlate with reality? So that validation is done using spatial metrics of these microstructures. Okay, obviously then comes the properties of interest and how are we designing the data set? And this is a critical step before getting into complex machine learning architectures. What is really important is how do you define the data? How do you design your experiments, virtual experiments here? Yeah, so that is the snapshot of this particular slide, in which we identified the practical range of properties and the input parameters in terms of the volume fraction and the fiber matrix combinations. Yeah, so that is what you say. For example, if I take this, let me open the pointer options. So if you look into this particular number here, the ratio of the fiber modulus to the matrix modulus, it goes from 2 to 200. So that basically tells you that pretty much covers the entire practical range that one would want to design. So that is what I mean. You make your design space as large as possible. That doesn't really mean you're cranking up the machine and then generating millions of data sets. No. Yeah. So that is not the point. The point is you have a wide range of design space, but still sample effectively so that you cover the range and choose a model such a way that it can interpolate well and also extrapolate to a reasonable extent outside the design space or the data space. Okay. These are some of the properties which are obtained using the so-called variational asymptotic homogenization, which many of you might not be aware of. But to put it simply, what we really do is we create RVEs, representative volume elements of arbitrary microstructures. And then what we do in one step, using this technique that I just mentioned, combining variational and asymptotic principles, we pose a variational statement of this RVE. And then by minimizing the strain energy density of this problem in terms of the small parameters that exist in this problem, we basically arrive at the Euler-Lagrange equation. And from there, you can get the effective homogenized strain energy, which would eventually result in the bunch of properties of your interest. And those are the homogeneous properties. I'm aware that I'm going faster in explaining this particular tool, but the reason why is this particular tool is already established. We have published papers, and you can refer to that. It's called variational asymptotic homogenization, originally developed by Professor Dewey Hodges and Professor Wenwen Yu, originally from Georgia Tech, and of course from our group at IISc, led by Professor Anusuya. Okay, great. So this is how the data set looks like. The Young's modulus, the thermal expansion coefficient, and the thermal conductivity. But also what is not shown here is other set of properties, such as yield strength, and also electromagnetic properties or piezoelectric properties are all data is available, but it's not shown here for brevity. Okay, great. And next key thing that we do, which is a very simple step but quite useful, is you need to make your machine learning model as objective as possible. In other words, if you show your model a given microstructure, however you rotate the microstructure or split the microstructure is still the same, right? So this is one way of augmenting the data, but also making the model more objective for these rotations or reflections. Yeah. Okay. The next key step is, so as I said, we have about 18,000 microstructures, not millions, 18,000 microstructures, but still we were able to populate the entire design space, covering arbitrary combinations of hybrid matrices, yeah, and arbitrary multiphysical properties. Yeah, some of them are shown here. So what we do as a key step is, in the microstructure, which is binary, it's a two-phase microstructure, you embed the material information, or you encode the material information as arrays. Yeah. So that during the training, these arrays are passed in. These arrays are input properties. So once you know the properties of the individual phases, you basically have different layers in your microstructures. One is the microstructure image, but then there are multiple other layers behind, which are the material properties encoded in arrays. Yeah, so that is what you basically see here. Okay, so with that, now what we have is material encoded microstructure and the resulting effective properties that is obtained in a computationally efficient manner using the technique that I described before. Now we go on, the data set is ready now. Now we go into CNN. Now in this part, one can think of a whole lot of architectures. Yeah, but the objective here, we choose one of the most popular CNN architectures, inspired from VGGNet type of architectures, quite popular in computer vision applications. So we used that and then adapt it to our problem here. One may argue other classes of architectures can also be quite useful here. For example, one of our organizers is quite active in working on neural operators. In fact, we have a project that is going on utilizing neural operators for these kind of problems. But the point here is not really to justify a particular type of architecture, but to show how the entire pipeline should be constructed such that you achieve the goal of having a more generalized model to predict a wide range of properties of interest. Yeah. Okay. So with that architecture, these are some of the training results that you see. Of course, the first step is what is the image size that one needs to take to achieve a reasonable balance between computational efficiency and accuracy. So that is what you see here. And we used, if you look into it, the image resolution, once you cross 128 by 128 pixels, you basically converge and you basically stop there. And that's enough. You don't want to arbitrarily introduce more and more computational complexity to the training process. Okay, so that is what you see here. And the other thing is, one is the image resolution. The other thing is the number of samples that you need. Yeah, so we have about 20,000 samples, but then in the end, what we really found out is you do not need the whole lot of samples. Yeah, so if you choose your data space wisely, as you can see, the convergence is achieved when the number of samples reaches more or less 10,000 samples, and that is what you basically see. And the properties of interest are Young's modulus, shear modulus, the thermal expansion coefficient, and thermal conductivity are what you see here. Okay. And with that, the next key ingredient in the whole process is how do you inform the physics that you have in hand? I mean, in micromechanical homogenization, the physics that you have in hand is, apart from solving the micromechanics, what we have is in terms of the physical bounds. Yeah, in other words, you have a microstructure, you have certain combinations of the phase properties, then that directly dictates this should be my upper and lower bounds for the properties of my interest. Yeah, I mean, one of the most popular bounds are the Hazen-Shingman bounds in two-phase composites. So what we do, we enforce these bounds as in a hard manner during the training process so that the model respects the bounds, because physically that needs to be respected. If you do not enforce it, you see that in all different data sets that we have considered, there are several samples in the order of hundreds which disrespects the bounds. So once you enforce it, we made sure that the model basically respects the physics that we have at hand. And this is very different from the popular physics-informed neural networks. That's a different story altogether. Here we are talking about a different way of infusing physics. Yeah. In other words, no governing differential equations are introduced as loss functions during the training process. So that is what I'm trying to clarify here. Okay, so once you have some sort of physics that is infused, which is quite important in homogenization, these bounds are should be met strictly. And some of the results are what you see here in terms of the error metric, absolute percentage error of different properties. But without getting into the details, what you really see here is for vast majority of the samples, the error is within 5 to 7%. Or to give better clarity, this is the error distribution. The AP is plotted as a fraction of samples in your test data. And as you can see, 90% of the test samples, you get an error that is within 5%, which is really good for engineering design applications. And what is really important is this error, even if you go to the highest error of about 10%, this has to be understood in the context of the generality that the model provides. Yeah. So here, the model is not for one particular fiber matrix combination. It is for an arbitrary fiber matrix combination and for arbitrary material properties. And that is quite important here. Yeah. So that is what you see here in terms of the results. Okay. So now, obviously, we have a design space for the data set generation. But then what if you extrapolate or you force the model to predict out of the bounds? And that is what we have three different data sets that you see, D2, D3, and D4, which are in the extrapolated domains, widely extrapolated domains, which are not physically needed for practical purposes because engineering design, they do not go into that space. But nonetheless, what we really want is we want to check how the model can extrapolate reasonably well. And of course, here the disclaimer is we are not extrapolating significantly out of the domain, but we still go reasonably enough out of the bounds, the design for the data. And what we really observed is, again, more than 90% of the samples in the extrapolated or extraterritorial regions still provided a reasonable prediction for the properties, as you see here, for all sort of properties that you can think of, both mechanical but also thermomechanical properties. Which is a good news. Which is a good news because the model is now not only generalized for arbitrary material properties and material combinations, but also it can extrapolate well in the neighbor domains outside its training space. Okay, now comes the other key ingredient in the framework. It's in terms of do I understand how the model actually learns? Yeah? So how do you do it? There are different approaches available out there in the literature. And here we used a very simple layer-wise relevance backpropagation algorithm in which, in layman terms, you basically dig into the architecture of your CNN and then see how the features are extracted by the model. And getting into the results, you see on the top left, a simple two-phase microstructure Yeah. And then what you really see after the digging in process within codes, you see different filters identifying different ingredients or features of the microstructure. For example, in one case, you see on the top right, you see the matrix face is detected. Here the fiber face is detected. Here the interface is detected. So these are the features that are extracted by different filters of the CNN. But what we do, we go one step forward to see how these features are considered important for the predictions. And that is where you see here we took two different samples from two different extremes of volume fractions. And what you really see is this particular contribution of those features. You see two main peaks. The peaks are reversed in the bottom two figures. The reason is in one case the volume fraction is high, and the left side the volume fraction is lower. Accordingly, if you focus on this particular graph, what you see is two peaks. One corresponds to the filter 13, which is the fiber phase. It identified the fiber phase completely, and the other filter identified the matrix phase, and you see those are peaked, which means the model considers these two features to be important in the predictions. It reverses here because the number of fibers are more, so you see the fibers are peaking here than the matrix. Obviously, you see many more little blips here, which means there are other features that the model extracted, but they are not considered to be really important or significant for the predictions. But if you want to extrapolate it for complex microstructures, such as what if the microstructure has pre-existing defects or flaws? In that case, those features might assume importance, and that is where you might see potential third and fourth peaks that might have an impact on the predictions. Yeah. So as a third step within this interpretation process is we also looked into can we get some insights into the physical model that it is trying to learn, and that is what the result you see here. The x-axis is the volume fraction of one of the phases, the fiber phase, and then the y-axis is the contribution of those two features, the fiber and matrix phase. And what you see on the left-hand side, the Young's model, is you see nonlinear variation, which is what you typically expect in a transverse Young's modulus for a two-phase composite. Yeah, so which means the physical physics is kind of learned during this process. Yeah, that is revealed through this interpretation. And also on the right is the plot for yield strength as a function of volume fraction. So here also we see there is a linear dependence of yield strength with respect to the volume fraction. That is also reported in some of the simplistic mechanics of materials based models for strength properties in a two-phase composites. So that is good. We were able to derive the physical models which the deep learning architecture is trying to learn in the first hand. Okay. Great. We also did a little work on take a realistic experimental microstructure. This is an optical micrograph of carbon fiber reinforced composite. So what you do, you clean up, you take different cropped images of those so that you can feed in. The only step that you do as a pre-processing is you convert them to binary images, and you can see the quality of the image is quite poor, but then we feed into the model and then see how it predicts. And what we observed is it predicts reasonably well. If you look into the non-dimensionalized Young's modulus, the experimental value is 3.63, whereas the predictions by the CNN is about 3.88, which for the poor quality of the image that you fed in, it's quite reasonable in my opinion. So that basically tells you the whole story in terms of how you design the data such that you cover the wide design space without necessarily making the number of data points to be millions or even more, but also infusing physics where possible and use computationally efficient technique to generate data, and also make sure your model is extrapolatable and your model is interpretable, and that is what you basically saw in the whole process. Okay, so now we go on to the second example, which is a completely different problem. Yeah, so here the objective is a surrogate model is developed purely for uncertainty quantification on the so-called lifetime of a novel material system. So here the material system is self-healing thermal barrier coatings. Yeah, which is typically found in aircraft engines. Yeah, so in the turbine blades, you see that. But to give a bit of background, a schematic of the thermal barrier coating is what you see here. It has multiple layers. Yeah. So imagine the bottommost layer is the turbine blade in your aircraft engine. These blades made of nickel alloys, they are exposed to 2000 degrees, and that's why you coat these nickel blades, nickel alloy blades, using ceramic layers. Yeah, that's made of yttria stabilized zirconia. But forgetting about the details, uh, what happens in such coated blades is that micro cracks form for multiple reasons. One is an aircraft takes off and lands, which means micro cracks develop because of the thermal expansion and contraction. And here we are talking about combinations of metals and ceramics. Naturally, they expand and contract differently, so micro cracks grows. But what is happening here, if you look into the thin black interface layer that you see, that particular layer keeps growing during operation. There's an active layer. There is another rich physics, which is driven by chemical process, diffusion reaction process is happening there. That adds material growth induced strains and hence stresses and hence crack evolution. So if you don't prevent it, these cracks coalesce, form a major crack, and then the ceramic coating falls off and it exposes the underlying metallic components. So that is where what we proposed here as part of the EU and Dutch government project is basically we incorporated healing particles so that without getting to the physical, let's say, physics of this particular problem, what happens here is these healing particles enable healing of these cracks. I'm not going into the details of that because that is not the purpose here, but you can refer to different articles that we published in this particular topic. So the idea is that we are rehealing this crack so that you can recover the mechanical integrity and hence extend the lifetime. But the problem is this is a highly complex material structure. You have multiple physics that are going on. You have complex microstructure that you have complex physics such as cracking, healing, material growth. So a lot of physics that are going on here. So how do you design such system? So that is where computational tools are quite handy. So what we really did here is we broke down the complexity and we established a modeling framework. From the concept, we want to get a design tool, a computational design tool, and you see a lot of ingredients are going to come in, which I'm not going to get into the details, but that basically tells you the complexity of the problem, whether it is the microstructure with spores and layered structures or crack healing, which is a physics in itself, the thermally growing oxide layer, which is a physics altogether in itself, but also multiple other interactions that you have in this complex system. So, but the objective here is we want to have a modeling tool that can predict the lifetime so that the material scientist can use that as a design tool to choose the design parameters of their material system. Yeah. To put it simply, you say that you have a healing system, yeah, self-healing system. How do you choose the particle size? How many particles do you need? Where the particles should be placed? What should be the size of the particles? What should be the spacing? These are all the questions that it's quite difficult to answer through experiments. Otherwise, you'll keep doing the experiments for years without getting into conclusion. So that is why modeling tools are useful. Without getting into the details, I'm directly jumping to the result. There's one snapshot of the fracture simulation that we did, incorporating all the physics that you saw in the previous problem. Yeah. Again, without getting into the details, what we really get out of that is we can predict how many cycles do you need to completely fracture the system, the coating. Yeah, so that is your lifetime. Okay, so for example, here without healing particles, the lifetime is 13 cycles, which in reality can correspond to 1,300 cycles. We did it in an accelerated manner. And if you put healing particles, the number of cycles are quite high. Yeah, so you clearly see there is a lifetime extension. But the problem is, even though you know that due to healing the lifetime will extend, you cannot control the ingredients in it, the design parameters in it. It's quite difficult to control. So you need to know which design parameters are quite influential in affecting the lifetime, so that the material scientist can design those parameters to optimize the system, right? So what we really did here is we did not build a surrogate model for the purpose of predictions. That's really important. but rather we build a surrogate model for the purpose of quantifying the sensitivity of different design parameters of interest to the material scientist, and we assess those so that you can give some useful guidelines to the scientist to develop these systems. Yeah, so which is quite different in than what typically machine learning models are used for. Okay, the pure reason for that is you see the statistics of crack evolution. It's quite stochastic in the sense that it's not really deterministic. Yeah. So, but what you really see is, as compared to this black line, which is without healing particles, if you put healing particles, the slope goes down, which means you're slowing down the crack growth and the number of cycles increases. That is the effect of self-healing. But then there is a large scatter. So how do you handle those scatter? Yeah. But then if you want to really do a multi-color simulation, it's quite impossible because each simulation took 60 hours in the high performance computing cluster. And we are talking about thousands of simulations, which we cannot really afford to do. So that is where we build a surrogate model purely for computational efficiency and quantifying the uncertainties of the parameters. Okay. So when I say surrogate model here, we are not bringing in machine learning here. We are purely talking about a polynomial chaos expansion based or PCE based surrogate, in which we chose 5 different design variables of interest, and then we pass it on to our complex simulators after sampling through Latin hypercube sampling technique. And then you train the surrogate, the PCE surrogate, for the lifetime. And then you basically interrogate the surrogate for the small design space that you are really interested in, and then look at the sensitivity of the different parameters. Because that is the whole purpose of developing the surrogate, not really to have this as a design tool to explore the whole design space. Yeah, because material scientists know they have this small design region which they are interested in, and that is where we want to show where or which parameter is more sensitive to the design or to the lifetime. Okay. Okay, so without getting into the details, we chose, let us get into the results without getting into the details. So these are the quantification of the sensitivity of different parameters, or in other words, the results of the surrogate model of the PCE for 5 different parameters is what you see here. But by looking at it, this was a useful result for material scientists. Why? Because you have 5 parameters that they think is really important. But then by looking at it, you see only the top 2 parameters are quite sensitive to the lifetime, whereas the bottom 3 are not as sensitive as the top 2. And that in itself is a useful result that computational scientists can feed to the material scientist, practically useful and valuable results. Okay, and of course you can look into the Sobol indices for the first order and the total sensitivity index of all the 5 parameters, which is also reflected. What I just told in the previous slide is also reflected here. The interface amplitude and the TGO growth coefficient are the primary contributors for the lifetime, which means the other 3 parameters, which are to do with the healing particles, are not that important for the self-healing system to be optimal, which is a useful result because material scientists do not have to worry about whether the particle diameter should be exactly 20 microns or is it okay if we have 16 microns or 24 microns. The answer is it doesn't matter. Go ahead. Yeah, so that's the level of confidence that you can get. On the right, you have the PDF function for the lifetime. Of course, the PDF gets more broader when you have this uncertainty included. So to quickly summarize here, you clearly see self-healing improves the lifetime, but with a large scatter. And that is where these surrogate models can come in handy to quantify that uncertainties and give some useful insights to the material scientist. Okay, so that's the second example that we saw. Follow up to the second example. What we really did is a toy exercises. So we used PCE as a surrogate, but then why not use the same data set and fit or train a Gaussian process regression? But what we really observed is you basically get the same result. So then the question is, do we need to complicate an architecture? Because if we are clear about the requirements, a very simple surrogate is using a simple architecture is more than sufficient. For example, here, use of a CNN is an overkill for sure, right? Because that is not really the purpose here. It doesn't really fit here. Whereas a PCE fits very well for this particular problem. Okay, whereas PCE might not fit for the problem that I had before, in which you have 18,000 microstructures of arbitrary material combinations that you can imagine. So that is where deep learning architectures are more applicable. Okay, now moving on to the third problem. I'm looking into the time. I see I have maybe, I'll try to finish in 5-10 minutes and then go to the final slide. So this is the third problem. It's what we really did. And I think this particular problem is a useful problem. The reason why is this. Without getting into the details, some of you might know what crystal plasticity is. If you do not know, classical plasticity such as von Mises or Tresca theories, they are phenomenological model that are applied to macro scale. Yeah. So in other words, they do not resolve the grain level details, whereas crystal plasticity, they look into slip systems and the activation of slip systems and how slip system grows and so on, or evolves. Yeah. So it's more high fidelity way of modeling plastic deformation in metallic materials. Yeah. But the point is these models, though they are really high fidelity, they're computationally expensive as opposed to the classical plasticity theories. For example, one simulation that you see here, thanks to my collaborator who did these simulations, it took a complete week in a high performance computing cluster. Yeah. But then when we dig deeper, what really happened is this is how a crystal plasticity model works. You have this state variables, like in classical plasticity, you increment your strain and then you basically update your state variables, primarily the plastic slip and the associated plastic deformation gradient. Yeah. But then these crystal plasticity equations are nonlinear, which means they necessitate Newton-Raphson iteration to solve. At each integration point in the RVE or in the material volume element, you need to solve at each material point the Newton-Raphson. Yeah, but also remember this at locally, but you have also the global solver that is in the finite element loop, the global finite element solver. So you have two different nonlinear loops running on, and that is quite time consuming. So what we really proposed here is not to build or replace the whole finite element solver as a surrogate with a surrogate, rather to replace this time consuming crystal plasticity with a user material that is driven by a data driven deep learning surrogate. Yeah, that's basically objective. So without getting into the details, let me show you some results. We explored different architectures and we found that LSTM is quite appropriate for this because these are all history dependent deformation, right? Plasticity. So that really worked well, as you can see in the metrics as well. With a very good accuracy, we developed a LSTM-based surrogate. And you see some of the stress evolution predicted so well for simple normal loading, but also for mixed loading, which you see here, also captured the evolution. It's not just predicting one property, it's the whole evolution of the stress strain response for arbitrary loading conditions. Okay, and also you can apply crazy load steps that you can see, still the model is able to reproduce or learn how the stress states will evolve. And this is a very good example because here we are not really replacing the solver itself. We are replacing one small part of the solver, which can be as generalized as possible. Because remember, at a material point, your problem is tractable because the only variable that you have is deformation gradient. If you cover the whole design space of your deformation gradient or data space of your deformation gradient, you're all set. And if your model is trained well on that, then you have a generalized user material or a constitutive model that can replace the expensive crystal plasticity subroutine within the global finite element solver. Yeah. Okay, that's good. Now, the final problem is for damage simulation. So before is plasticity, which is a nonlinear physics. Damage is also another nonlinear physics. Without getting to the details, I'm going to show you 2 slides and jump to the conclusions. So in here, what we really did is for a very simple problem, a plate with arbitrary crack topology, can we predict? And that is what you see here for one example, but also for different, the classical claim is if you develop a surrogate to predict this evolution. So these are all not just one-shot prediction, they are time series based prediction. In other words, it can auto-regressively, it can predict the whole evolution of the crack path throughout the process if you're providing the time-based boundary conditions. Yeah. So the claim is yes, it's computationally very, very fast. But the point is it really useful? Of course, we expanded it for arbitrary crack topology, and it works really well. It really predicts very well. But the point is this a useful application? Yeah, in my opinion, it is not. The answer might be obvious because what if you change the boundary condition? What if you have inclusions in here? So this model, to make it more generalized, it's quite tricky. Yeah. So that is where I say that this type of developing surrogates for a very narrowed applications is not that useful, but it can be a benchmark problem, obviously, to test different architectures. And that is what we basically did here. Okay. So upon reflection, we discussed 4 applications, yeah, using different architectures for different range of material problems, ranging from microstructure property correlations, quantific uncertainties in self-healing systems, crystal plasticity modeling, and fracture simulation. Yeah. And my question is, which ones are more useful than the others? Yeah. And some of you who are listening here, it might be very obvious. For example, in my opinion, the first one here, that is more useful because why it is useful? Because we try to make it as generalized as possible. Yeah. In other words, it is applicable to a wide range of material systems, and that is what we need. Then it becomes a design tool. Okay. And then this one is also useful in its limited scope. Yes, remember here we build a surrogate based on PCE, not really to replace the entire physics-based solver, the multi-scale solver that we've developed, which is really high fidelity, time consuming. But then we use surrogate in a way that resolve or solves our purpose, which is to quantify uncertainties and to quantify the sensitivity of different design parameters that is of interest to the material scientist. And crystal plasticity, I believe it's one of the very good examples of using machine learning architectures because we are looking at a material point. We are not looking to the entire domain that you're trying to solve. And we are not trying to replace the entire solver. We are trying to replace one particular part of the nonlinear solver, not the global nonlinear solver. And then that can be as generalist as possible. And that is what we have solved. And for now, this is a work that is ongoing, that is not really nowhere near completion. We use graph neural networks to predict the fracture paths. But that at this stage, I do not think that is really useful for obvious reasons, because it is not generalizable. It's not applicable to a wide variety of problems. Okay. So the outlook is it's really important to identify appropriate mechanics to treat using machine learning, and also identifying the scales at which you want to deploy your machine learning is important. And some of the key things to be considered is how would you make your model as generalized as possible? And where possible, how would you infuse physics? And obviously, can you understand how the model is learning? Having said that, I think one thing that we really need to answer is one of the slides that I showed before. Answering those 4 questions is really important for the way forward to make these tools a useful ingredient in the computational mechanics community. So with that, I would like to thank you all the contributors to this work. There are a few others who are not listed here, but then these people are key contributors, and also I acknowledge my funders and my collaborators. Thank you so much. I think I exceeded the time by 5-10 minutes, I guess, but nonetheless, thank you so much for listening.
That's fine. That's not a problem.
Thank you so much, Satish. Really brilliant piece of work. And I think those 4 questions really spot on. I think we had a few questions from audiences in the previous seminars where they were asking questions that what kind of tool to use. I think more important than the tool, that you set the problem right. That is one of the very important questions that one has to get a good judgment on at the outset. And only then that I think that tool can be then selected. Very nice presentation. So with that, I think I'll go to the audience if anyone has any question. Yes, Dibujyoti, I can see. You can please go and unmute yourself and ask a question.
Hi, Dr. Satish. So, I mean, thank you for the very nice talk. I had like a couple of questions. So, the first is regarding the usage of GNNs for fracture simulation. So, you mentioned, I think that you do not find it useful. Is it because of varying boundary conditions enforcement? I mean, is that the challenge, or what was the main challenge?
Okay, so let me quickly decode that. So use of graph neural networks is ideal for fracture problems because we are dealing with finite elements, and it goes really well. So no doubts on that. That is why we chose graph neural networks. So graph neural networks is really useful for fracture simulation based on mesh topologies. But the reason why I said it is not useful is exactly the point in which the data set that we designed is not generalized enough. In other words, if you change, so what we saw here is all edge cracks, multiple orientations. But what if you have a little pore or a pre-existing defect elsewhere, Or what if you have inclusions? And what if your boundary conditions are quite different? And what if you don't just have a simple plate? How would you scale it to realistic problems of interest? So that these questions make these models to be really useless. Whereas in some cases in which your boundaries are tractable, for example, if you look into the crystal plasticity, remember, crystal plasticity can be used to simulate even large scale structural problems. But of course, time consuming, it would consume months of time. But the point is, we are carefully ignoring the variables that you can't really track. For example, what if you have a curved panel of a car that is deforming plastically under impact? We do not worry about that. What we are really interested in, you have millions of material points, integration points are there, and at each integration point, you are running a neutral adaptation iteration, and that is what we are trying to replace. So we're not trying to replace the global solver that is solving the structural topology there. So then there it becomes useful. Yeah. And the other problem is microstructure. Also, the reason for that model to be useful is because the way we constructed the pipeline is as generalized as possible. For example, if you look into lots of manuscripts, the initial manuscripts, including the one that we published back in 2019, that one is only applicable to carbon fiber composite. Then my question is, what are we going to do with that model, right? I'm looking at the screen because I'm seeing you here, so that's why I'm not looking here. So that particular model is restricted to one material system. So what is the design there? I mean, we can't design anything there. The material is fixed. The only thing that you can change is the volume fraction. Yeah, but we already have existing models for that. And also that particular paper, we looked at a couple of properties. Again, it's not useful. Yeah, so these sort of questions that we need to answer before choosing the architecture.
Right. So it's, I mean, so the takeaway that I can have is basically use the surrogates as some like to basically replace a certain part of your solver, but you have your global solver just so that you can account for different, I mean, conditions.
Yeah, in other words, it's just one simple question. In any complex computational mechanics, there is always a smaller problem, meaning, let's say, in a global picture, there is a small module that is nonlinear as well, but then that problem is well defined in terms of its boundary. Yeah, I mean, at a material point, what you can supply? You can supply any arbitrary deformation gradient, but then the deformation gradient is well defined. Of course, the data set has to be, so for example, we considered 10,000s of deformation gradient, obviously, but then it's still defined. Whereas if you look into a structure, it's completely undefined. You have structural topology, you have combination of materials that are possible, you have arbitrary boundary conditions, that is simply not tractable. So that is where machine learning would fail because, for example, if you look into, if you're trying to develop a surrogate for flow predictions on an aerofoil, in my opinion, is it really useful? The question, I mean, the answer lies how generalizable for arbitrary aerofoils and for arbitrary boundary conditions. If the answer is yes, then yes, it becomes useful. Yeah. So yeah, that is what I primarily intend to convey.
And my last question is basically in your microstructure problem, you mentioned that you enforced physics in a hard way for the HS bounds. So did you design the loss function to like automatically satisfy the HS bound, or how did you exactly do that? Because that was unclear to me.
Yeah. So in the classic, so we also worked on the other aspect in which one of my students who did that work, he tried to look into using an alternate version of physics-informed neural network to solve the problem itself. I mean, and there are existing works on that, even from Johns Hopkins University as well. But what we thought there, because we have a computationally efficient tool that solves the physical problem, and we have a design data set that is sufficiently large enough or wide enough, we do not have to adopt a physics-informed neural network in which we do not have loss functions that solves the differential equations in the domain of interest. Yeah. Rather, what we did, okay, we have the physics that exist in the wide data that we have. So let us not worry about that in terms of the governing equations. Rather, what we really know is we have this physical constraints in terms of the bounds. The classical one is Hazen-Brinkmann bounds. Can we respect that? So what we did, we basically normalize our properties, the effective properties, homogeneous properties that we are trying to predict, and we make sure the predictions fit within the normalized bounds. Yeah, so that is how it is trained, and yeah, because we saw, so out of 18,000 microstructures, it's only hundreds that violated that, but we do not want that, and hence we enforced it. Yeah, so it's not really fully physics informed, so that's why it's infusing some physics that you are certain of.
Right. So it's just a hard enforcement, not through the loss function
no,
as such. Yeah.
Exactly.
Okay. Yeah. Thank you.
So I think I had a very similar question as Dibyati had regarding the same thing, enforcement of those bounds.
Right.
And I was trying to think, like, how are we enforcing the bounds? Was it being enforced in a hard manner in some, or is it being soft constrained in a like a hard manner? So which means that in this case, that hard manner in which you're actually doing it, you're like, if these certain material design is actually exceeding those properties, you're just kind of rejecting those designs. Is that the case?
During the training process, yes. But in the end, once it is done, then it respects it in a hard way.
So it is much like you are just rejecting. So it's like a sampling kind of thing out of the many designs, a few designs which are actually coming out of those, not satisfying those bounds, you're just rejecting them and then resampling again to just see. Okay, got it.
Exactly.
Yes. I think, Somnath, I have a question, I think.
Yeah, I have a lot of questions. Wonderful presentations, Satish. I really enjoyed all the 4 examples.
Thank you so much. But I had to rush through because I couldn't spend, because each one is easily a 30-40 minutes presentation. So, but thanks for that.
I think your group and my group has like enormous amount of overlap. We are looking into all these problems that you typically brought up. So I'll just quickly run through a few of the questions I had. The rest I'll follow up on an email. So with the microstructure problem that you mentioned, actually, that's what Divyajyoti was asking, we actually came up with a GNN architecture. So not to say a GNN, but a GNS architecture, where what we are doing is we have been able to generalize it really well in terms of different not boundary conditions, I would say. It'll be in different like initial condition problem. So we've been able to generalize it pretty well. And I was wondering if your microstructure problem could be an example over there, because what I saw is you have your fiber had different shapes. So if you are using a CNN, you are quite restricted by the shape of the full domain, as well as a very high discretization to represent your fiber. So do you think GNS could do a better job there, or GNN in general? Have you given that a shot?
I mean, not yet, but for sure that is potentially a clear direction to go further. For sure, but we haven't really explored that direction. Though we are using graph-based approaches for other sort of problems, not in the microstructure. But yeah, I'm more than happy to discuss later. And if it is a quick marriage between the existing tools, why not? I think that would be fantastic.
So I think the paper that you were referring to, which was from Johns Hopkins, was probably Professor Graham Brady's paper.
That's right.
Okay.
I mean, we met at EPFL Switzerland because he was on sabbatical.
He was on sabbatical. Yeah, absolutely.
I was on mine in a way at the same time. So.
Oh, okay. Okay. So you had an overlap.
Yeah, indeed. Yeah.
And I was wondering, like you mentioned, you are using neural operators. Do you see any difference between the efficiency of a neural operator against using standard neural network architectures?
I think the guy who raised the hand, Sauvik, is the person to answer this question because he is leading the work.
I did not raise hand. Santanu, I think, raised hand.
Okay. So that particular work, to just clarify.
So, 2 SCs, one Sauvik Chakraborty and one Santanu Chaudhary.
Okay. So, in fact, we are presenting that work in the conference that is coming in Bristol. It's AA-Comp, or AA for Composite Materials Conference. So that work is primarily led by Sauvik, and the way we we worked is basically because we have this nice data set and we want to explore other sorts of architectures, like exactly what you said now with GNS. Can we do something together? It is in that spirit that I contacted Souvik, and we know for a different reason before. So we thought, let's try to see what it can offer. It does promise something, but then since still the work is not complete, so I don't want to come to any conclusion now, which might go, which may not go well. So I don't want to give any conclusion now, but probably in few months' time, once we have concrete results, if I say the project is complete, then I would be confident to comment on that. But we are currently working on it indeed.
Yeah. Okay. And maybe just like a last question remaining,
Sure,
I'm
sure.
going to send you an email. You talked about crystal plasticity and you're trying to replace the Newton-Raphson or the inner nonlinear solver while coupling.
Exactly.
Did you do a real-time coupling, or is it like you are keeping the model trained and then you are coupling it separately with the finite element solver?
Yeah. So it's a pre-trained model, but the way we framed the problem, this is also part of the grant that I talked about before. So the way the grant is written, which is always ambitious. So for now, what is achieved is a standalone user subroutine, or the constitutive model is what we have here, that can be coupled with the global solver. So the work that I haven't presented is that coupling is not done yet. But since the model's accuracy and the capability to predict for unseen deformation gradient is quite powerful, I believe that that particular integration would be straightforward is my thinking, but I have to see once we integrate it. So far what we have is, in the context of abacus and answers, we have this UMAT that is quite fast.
Yeah.
So the point here is, it's quite difficult to integrate in the existing commercial finite element codes for obvious reasons. So that is for example, in the fracture problem that you see towards the end, we are using Akan2, if you've heard of, that's developed by Professor Gianfranco Molinari at EPFL.
Yes.
So that is the framework that you're using. So that since that is open source, we are able to control what we can replace. For example, there, so Akan2 is a phase field fracture problem, a fracture simulator. So there, the approach that we take is, we want to replace the phase field equations or the solver, not the linear elastic solver that wraps. Because we did those training for predicting the stress strain fields in any arbitrary structural topology, but we found that to be inefficient for the reason that running the linear elastic solver is quite straightforward anyways. But what is really taking time is the solving the phase field variable. So the objective is to replace that alone and keep the global linear elastic finite element solver as it is.
Right.
And since it is an explicit solver, it's quite easy to integrate these two things. And that is the work that is going on. In fact, my PhD student is traveling to EPFL in few days and spends few weeks there with EPFL group. Yeah.
Satish, actually, in our group, we have something called like a domain decomposition based coupling solver. I would be happy to forward you that paper. We got that recently accepted. So what we did is like the main idea is that we want to replace the locations which require very fine mesh with a physics informed neural operator, and the portions that are good with coarse mesh, we let the finite element solver run over there, and the two solvers get married with the alternating.
Cool. How do you ensure, because you're looking to two spatio-temporal domains, right? In a way. So how do you interface?
So we have an interpolation scheme, and we are coupling it with that interpolation scheme along with the solver scheme. So
and is it explicit or implicit?
Explicit.
Okay. That takes some of the difficulties.
Yes,
exactly.
Exactly.
Okay, that's good. But I would be really keen to discuss that, probably in a separate call.
Yeah, absolutely. And we are trying, like right now, that was a proof of concept, which when we started, we didn't think it would be so hard. Initially, we thought physics informed would be easy, but then it brought its own complexities with like generalization and other stuff. We could only do it with Phoenix. We haven't been able to do it with COMSOL, Abacus, because of the inherent structure of how do we change it in the inner domain, inner solver. But yeah, I'm very happy to go ahead and send you the paper and have a separate call.
Sure, definitely. I mean, clearly you're able to comment on all the four, which means there is a clear overlap. Let's really discuss.
It's a huge overlap. Yeah. Thank you so much for the presentation today.
Thank you. Glad that you liked it. Thank you.
I have a follow-up question because I think I had a very similar question.
We can ask Santanu, right? He is raising hand.
Yes.
Hand is raised.
Okay.
Yeah. Hi, Santanu.
Santanu, you there? You're muted.
Yes, I'm there. Sorry. So Satish, fantastic talk. I'm Shantanu Chaudhary. I'm a professor of University of Illinois and from Argonne National Lab. But I'm right now in Thermax as CTO just for some time, just to spend some time outside. So your talk is fantastic. We come from the very lower end of the length scale. So the multi-scaling comes from the atomistic size up to the mesoscale. So it's a very complementary work. So I'm always very inspired by the developments you guys have made, because we make problems more expensive, and if somebody can make it smaller and reduce the dimensionality of the problem, it's very inspiring. So my question will be that we have another physics, of course, physics informed and physics integrated multi-resolution is a more complex version of the problem. So we have, for example, in a crack problem, a propagation problem, a part of one of our Air Force multi-university research initiative, it's a MURI, where we have surface free energies for crack propagation. So as the cracks open, as you know, the velocity and the stress fields and the plasticity, all those things are correlated with respect to, and on top of that, some of these models are also reactive. So there are kind of reactions going on at the crack tip. But let's say that let's forget about the reactions problem and get the problem at lower temperatures. So these are brittle metals. So do you have any ways of integrating surface free energies to determine which direction the crack will propagate and at what velocity? Because you're opening two surfaces and so on and so forth. You know all the detail, but just a quick check I can write to you in more detail.
Yeah, sure. I mean, clearly the problem is extremely complicated in my opinion. To deal with physics-based tools, forget about machine learning-based approaches for obvious reasons, because I'm generally, in other words, I quite find it very unconvincing to deploy machine learning architectures for highly interactive multiphysics problem for obvious reasons, right? Because you need to satisfy all the physics.
Slows it down, first of all.
Yeah, exactly. So coming to your point, yes, we have, for example, we used in a microstructure problem in which you have interactions of process zone, plasticity, and fracture and inclusions. We have developed the so-called configurational forces integrals, and which is basically a vector in a way. To put it very simply, imagine that it is a J integral vector. Yeah, which is basically
and I need a reference frame. I need a reference frame because all of these are Miller indices and planes and crystal planes and all those things, right?
Yeah. So we have a configuration force concept that is extended to deal with problems of high heterogeneities along with the physics that is plasticity and fracture interacting in the presence of any process zone. So we have that. I can have a separate discussion to see if that can be
if it can be tweaked.
And the thing is, the beauty of that configurational force integral, it's basically a crack driving force vector. And then, as you know, the crack driving force has to be, I mean, the direction of the crack driving force should be the direction of the crack extension according to the maximum energy dissipation criteria. So if you follow that approach, it should directly give you the crack direction. You do not need a separate criteria for crack extension direction or crack propagation direction.
Right, but in some sense, if you provide a physics penalty of some sort and try to say that you're trying to minimize the free energy and trying different orientation for the crack propagation, and you have some form of, I will call it reinforcement learning, but it can be, GAN of some sort. It can be written in different ways. Do you think that there is a way to impart machine learning into the propagation itself that minimizes the total energy that is released by the crack.
Yeah.
So it minimizes the total work done.
Yeah, so this is exactly the problem that my PhD student is working on. I mean,
Great.
So
okay,
we can discuss. So
yeah, absolutely. No, I just
formula
wanted to
is
put
done,
that.
but he is implementing it. So let's see, maybe in a month or so,
I'll drop
we
you a
should
line.
be able to comment on that confidently. Yeah.
Absolutely, great idea. Thank you.
Sounds good. Thank you so much for the question.
Thank you, Shantanu, for joining in. I have one question, which is basically, I just try to understand that where you actually substitute the LSTM for doing the Newton-Raphson. What is exactly that the LSTM is doing?
Yeah. So So this is, imagine a global finite element solver, which is nonlinear on its own. Whether it is explicit or implicit doesn't matter. So there is a global nonlinear solver at the global finite element level. But then at the material level, typically if your material is linear elastic, it's a straightforward thing. You pass on the strain increment, you update the stress, and then you pass it back. It's a simple linear process, one-step analytical calculation, because multiplying X models and then send it back. But in this case, it's not a homogenized model. It resolves the grain level details, meaning you have to look into which slip systems are active. If they are active, how much the slip have evolved, meaning what is the accumulated plastic deformation gradient. So to calculate that, you need to solve the field equations, which is crystal plasticity based field equations, which is nonlinear on its own. Yeah. So that nonlinear equation, you solve it using Newton-Raphson at each material point or at each integration point in the global finite element solver. Then comes the global nonlinear finite element solver. That's a different story altogether. So the objective here is at each integration point, which is subscale of the global problem, we want to replace that using a data-driven UMAT or user subroutine, user material subroutine if you want, which replaces this Newton-Raphson based solver for the crystal plasticity. In other words, you work with the same variables, you predict the same output state variables, but instead of solving the Newton-Raphson manner, you basically use this pre-trained LSTM based surrogate that auto-aggressively predicts the evolution of stress, but also the evolution of the state variables. Yeah. So you're not really doing any iterations over there. It's one-step prediction.
I see. So it's basically pre-trained and it's supposed to solve and mimic a Newton-Raphson solver.
Exactly.
Okay, nice.
Yeah.
Okay, interesting. Okay, thank you so much. So Souvik, I think you had a question.
Yeah, I have a very small question actually. Yeah, hi.
Hi, sir.
For the CP one, right, the crystal plasticity one. So how well is it generalizing? I mean, did you, for example, test it on, let's say, train it on BCC and tested it on FCC or those kind of things? Did you try it out?
That is a good question. So this one is limited only to BCC.
Okay.
Yeah. So the reason why I call it generalized is because you know what kind of material systems you're working on. So especially when you want to simulate crystal plasticity based simulations, you're primarily looking into microstructures. And if you know it's BCC and if you know that it works for any deformation gradient, then it's already generalized for that particular material system, right? So which means it's a useful surrogate.
Got it. Yeah. And I will talk with you separately regarding the first slide. I mean the optimization slide, the payload patent, right?
Sure.
So I'll talk with you separately.
Oh, definitely.
That might take some time. So I think with that, we don't have any other questions. So I will thank you once again for your time and giving this wonderful talk. With that, that's a wrap for today. Thank you everyone for joining in.
Thank you so much, everyone, the audience, and also thank you, Souvik, Rajdeep, and Samrita. Thank you so much. And I have to rush through the 4 different presentations, so apologize if you didn't understand some of them, but feel free to get in touch, and I'll be happy to have a discussion later. Thank you so much.
Thank you, everyone. Yeah, see you next week. Bye.
See you, Souvik. See you.
Thank you.